We've talked already about what it means for two events to be independent and what it means for two random variables to be independent. Let's look a little more closely about what that means for the cumulative distribution function and the probability density functions. So recall that random variables x and y are independent if knowledge of one does not influence our opinion of the other. Equivalently, we could say the probability that x is in some set A and y is in some set B equals the probability that x is in A times the probability y is in B for all sets A and B. In particular, that means that the probability that x is less than some value and y is less than some other value equals the probability that x is less than this value times the probability that y is less than that value, which we could write as f of little x little y equals fx of little x fy little y. And we can also write this in terms of the probability density functions. This implies that f of xy is going to factor as the marginal probability density function of x times the marginal probability density function of y. Or if we have discrete random variables, the probability mass function factors this way. And all of these should be for all values little x and little y. So for example, let's consider the joint probability density function f of xy equals 2e to the minus 2y e to the minus x. If x is at least 0, x and y are both at least 0. And 0 otherwise. So we showed in the last lesson that this factors as the product of the two marginal density functions, where the x marginal density function is e to the minus x or 0. So e to the minus x if x is greater than 0, greater than or equal to 0, 0 otherwise. And the y marginal density function is 2e to the minus 2x, y. If y is greater than 0 and 0 otherwise. So we can see that these two functions multiply together to give us this function here. Although we really should be a little bit more careful than this. So we want f of ab to be fx of a times fy of b for all real numbers a and b. So for a and b greater than or equal to 0, this is obvious. Because we have this definition when x and y are greater than or equal to 0, and these two definitions when x and y are greater than or equal to 0. But let's just check what happens if one or both of them are negative. Actually, if they're both negative, I think that's obvious too. Because then we're in the bottom case. 0 equals 0 times 0. So let's quickly look at what happens when x is greater than or equal to 0 and b is less than 0. So f of two numbers is this function if both of those numbers are greater than or equal to 0. If one is less than 0, then we get 0. And let's look at the product fx of a times fy of b. If a is greater than or equal to 0, then we have this formula, e to the minus a. And if b is less than 0, then we have 0. All right, so 0 equals 0, that's good. And what happens if a is less than 0 and b is greater than or equal to 0? So f of a b equals 0 because we only get this formula if both of the numbers we're plugging in are greater than or equal to 0. And now fx of a times fy of b is, since a is less than 0, then we get 0 here. And since b is greater than or equal to 0, we get that formula, 2e to the minus 2y, but it doesn't matter because we're multiplying it by 0. So 0. So we do get actually the same thing when we plug a and b into f and a and b separately into the marginal density functions. You can see you have a glare here. This says fy of b. So actually there isn't anything there that you're missing. All right, now just so that you don't think that every joint probability distribution function is for two independent random variables, let's look at one where the two variables are actually dependent. So let's let x and y have joint probability density function f of xy equals 1/2 if x is greater than or equal to 0, y is greater than or equal to 0, and x plus y is less than or equal to 2, and 0 otherwise. Alright, first of all, to see that this is a probability density function, we can see it's always positive because it's either 1/2 or 0. It's always non-negative. So to see that this describes a region that has volume 1, let's draw it. So we'll draw the xy plane looking down from above. So x plus y less than or equal to 2 is the region below this line. And of course, x greater than equal to 0 and y greater than equal to 0 means we're in the first quadrant. So it's this triangle. Let me divide this up into, so this square and then two smaller triangles. So this is a triangle of area 2, because we can see one square and then 2 halves of another square, so that's 2 total. And then the 1/2 means that in 3 space, if the z-axis is coming straight out at us, then we make a prism which has thickness 1/2, and 1/2 times the base of 2 gives us a volume of 1. So the region is a triangular prism. Of thickness 1/2. So the volume equals base times height, or base times thickness, which is 2 times 1/2, which is 1. Okay, so we do have a region of volume 1 here. So since x and y have this joint probability distribution function, we're saying that predicting x and y is like choosing a point x naught, y naught, z naught in the prism and recording just the x coordinate and y coordinate. Alright, so to see that x and y are dependent, let's consider the probability that x is less than or equal to 1, the probability that y is less than or equal to 1, and the probability that both x and y are less than or equal to 1. So the volume corresponding to x being less than or equal to 1 equals, so we have this region times the thickness of 1/2, so this is 1.5, 3/2 times 1/2, which is 3/4. And the probability that y is less than or equal to 1 is basically the same thing, except instead of using this triangle here, use that triangle here. So this is a base of 3/2 times a height of 1/2, which is 3/4. But the probability that x is less than or equal to 1 and y is less than or equal to 1 is, so x and y are both less than or equal to 1 if we have just this small square as the base. So 1 as a base times 1/2. But 3/4 times 3/4 is not equal to 1/2. Nine sixteenths is close to 8/16, but it's not equal. Alternatively, we could look at the marginal density functions for x and y and see that they don't multiply together to give us this density function. So alternatively, let's compute the marginal density functions. So the x density function is what we get when we integrate out all of the y's. So y is going to go from 0 to 0 to this diagonal line. This is y equals 2 minus x if we write it as a function of y. So y is going to go from 0 to 2 minus x. And then we're integrating 1/2 dy. So that equals y over 2 evaluated from 0 to 2 minus x, which is 2 minus x over 2 minus 0 over 2. So it's 1 minus x over 2. And similarly, if we want the density function, the marginal density function for y, then exactly the same integrals with the variable switch is going to give us fy of y equals 1 minus y over 2. Now technically that is for, I'm running out of space here, but the x marginal density is 1 minus x over 2 if x is greater than or equal to 0 and it's 0 otherwise. The y marginal density is 1 minus y over 2 if y is at least 0 and it's 0 otherwise. So I guess if I'm being very, very careful, I really should have written the integrals down here. The integral from 0 to 2 minus x 1/2 dy if x is greater than or equal to 0, y is greater than or equal to 0, and x plus y is less than or equal to 2, and 0 otherwise. If you like the integral from 0 to 2 minus x, but it's going to be 0 anyway. So integrating both of these parts over the correct domain, and then we end up with these two marginal density functions. Alright, well let's compare, does this product equal that? Looks like if we're outside of the region, we'll get 0 times 0 equals 0, so that's fine. But the problem is if we're inside the region, it's not going to work out correctly. So do we have f of xy equal fx times fy for all x and y? The answer is no. And we can see that by trying x and y equal to 1, 1 at this point. So f of 1, 1 is 1/2, but fx of 1 times fy of 1 equals 1 minus 1/2 times 1 minus 1/2, which is 1/2 times 1/2, which is 1/4, which is not equal to 1/2. So therefore, x and y are dependent. Alright, let's go back to an example where the variables are independent. So let's choose two real numbers. Independently and uniformly on the interval from 0 to 12. So let's say the real numbers are x and y. So x is uniform on 0 to 12 and y is uniform on 0 to 12. Let's find the probability that the numbers differ by at least 2. Now this is the probability that x minus y is greater than or equal to 2 plus the probability that y minus x is greater than or equal to 2. The absolute value here is because we don't know whether x is going to be bigger or whether y is going to be bigger. But by symmetry, these are both the same. We've got the exact same distribution. We could have called this one y, we could have called that one x. So this is 2 times the probability that x minus y is greater than or equal to 2, which I guess we could express as 2 times the probability that x is greater than or equal to y plus 2. Now, since we're assuming that these are chosen independently, the marginal distribution of x is 1/12 for x between 0 and 12. And 0 otherwise. And fy of y is the same, 1/12 if y is between 0 and 12, and 0 otherwise. So the joint density function is 1/12 squared if x and y are between 0 and 12, and 0 otherwise. Alright, now how should we integrate this to capture the fact that x is greater than or equal to y over 2? So if x is greater than or equal to y over 2, is y plus 2, then I guess x is between y plus 2 and 12, and y is between 0 and, I guess it can't go all the way up to 12 because an x couldn't be 2 bigger than it. So I think the biggest that y could be is 10, if x is going to be 2 greater than it and still less than or equal to 12. So we want 2 times the probability that x is greater than or equal to y over 2. 2 times the integral from, let's see, so y will go from 0 to 10, x will go from y plus 2 to 12, and then we're integrating 1 over 12 squared dx dy. So that's 2 over 144 on the outside because these are just constants. The integral is y goes from 0 to 10 of the integral dx is just x. X is going from y plus 2 to 12. So we have 12, let's see, 2 over 144, integral from 0 to 10 of 12 minus y plus 2. And this inside part, I guess we could write as 10 minus y. Alright, then we integrate that dy. 10y minus y squared over 2, evaluated from 0 to 10, is 2 over 144. 100 minus 100 over 2, 50, and then when we plug in 0, that's just 0 and 0, so this is it. So that's 2 times 50 over 144, which is 100 over 144, which we could reduce if we divide by 4. This is 4 times 25, and this is 12 times 12. We divide by 4, then we get 25 over 3 times 12, which is 25 over 36. So that's the probability. I did multiply by 2. That's the probability that the numbers we choose will be at least 2 apart. Alright, now I want to state a result about independence which is a little bit stronger than the factorization facts that we started with. So let's let f of xy be the joint probability distribution of x and y. Now if f of xy factors as some function of x times some function of y, for any functions g and h, and for all values of x and y, then the random variables capital X and capital Y are independent. Now little g and little h don't have to be the marginal density functions exactly, but they're going to be off only by a constant. So g of x and h of y are multiples of the marginal density of x and the marginal density of y. So to prove this, let's suppose that f of xy factors as g of x times h of y. Then we know that the integral of f of xy dy dx from both of them from negative infinity to infinity equals 1. But this factors as g of x times h of y, so we can rewrite this as the integral as y goes from negative infinity to infinity h of y dy times the integral as x goes from negative infinity to infinity g of x dx. And this is a product of numbers that equals 1. They're both positive numbers. So let's write this as a, b. So this integral here is a, and let's say b is this integral here. then the marginal probability distribution functions are, so the x marginal function is, we'll integrate out all the y's from this, which is just a product of h and y and g of x dy. Now g of x is just a constant, so we can bring it out. And we said that the integral of h as y goes from negative infinity to infinity is a. So this is g of x times a. And similarly, the y marginal density function is the integral as x goes from negative infinity to infinity of h of y g of x dx. H of y is just a constant if we're integrating over x dx. We can pull that out, but then the integral from negative infinity to infinity of g of x is some other number b. So this is h of y times b. So that means if we multiply together the two marginal density functions, we get g of x a, h of y b, but a and b are two numbers that multiply together to give us 1. So this is 1, and we get g of x times h of y. But g of x times h of y is just f of xy. So knowing that f of xy factors as a product of these two functions tells us that it also factors as a product of the marginal distribution functions, and therefore x and y must be independent. All right, now this result looks very innocent. It's only slightly different than the other factorization results we had before. The difference is we don't have to know that ahead of time that these two factors are marginal density functions. In fact, they're not necessarily going to be. They could be off by a constant. Nevertheless, it's a little bit tricky to apply. Let me explain why this is a little bit tricky. And I'll rewrite the claim. So, caution. So the claim is if x and y have joint PDF f of xy, which factors as g of x times h of y for all x and y, then the random variables capital X and capital Y are independent. So it's the for all x and y that's a little bit tricky. And let's go back to the example of a joint distribution function for random variables that are dependent. So if x and y have the joint probability density function f of xy equals 1/2 if x and y are greater than or equal to 0, x plus y is less than or equal to 2, and 0 otherwise, then x and y are dependent. Now that seems to contradict the claim here, because the density function 1/2 doesn't have any x's in it, doesn't have any y's in it. So how could it possibly fail to factor as function of x times function of y? But in fact, 1/2 does fail to factor for all x and y real numbers. So let me draw the region again. So here's the line y plus x equals 2, 2, 1, 0, 1, 2. And let's consider the points 3/2, 0, 0, 3/2, and 3/2, 3/2. So f of 0, 3/2, this is part of the region. So we get 1/2, 3/2, this is 3/2, 0, 0, 3/2 is there, but that's also 1/2. And then f of 3/2, 3/2, that's outside of the region. That has value 0. So let's suppose that f of xy factors as g of x, h of y for all xy. So then g of 0, h of 3/2 equals 1/2. G of 3/2, h of 0 equals 1/2. And g of 3/2, h of 3/2 equals 0. Well, if g of 3/2, h of 3/2 equals 0, then one of these two things has to be 0. But if g of 3/2 is 0, then that contradicts this first equation, where we have two numbers multiplying to be 1/2. And if h of 3/2 is 0, that contradicts the second equation. So we have a contradiction here. And it has to do with the boundary of the region. And we're not just looking at the non-zero part of the function here. We have to look at the 0 part also. So that's why that's a little bit tricky to apply. The end.